Good morning. Today we're going to talk about Chapter 3. Start talking about Chapter 3 today, which is entitled Systems of Equations. And in particular, I want to talk about Section 3.1 just a little bit, but mostly is 3.2. Section 3.2 is entitled Solving Systems of Equations Algebraically. That means doing algebra type things to the systems to come up with a solution to the system. Alright, what do I mean by a system of an equation? Well, let me further specify in section 3.2 we're going to be talking about 2 by 2 systems, well, meaning we're going to have two equations with two unknowns that I want to solve for simultaneously. For example, let's say I ask us to solve a system that looks like this. I'm going to give you two line equations in standard form. X plus 2y equals 4 and 2x minus y equals 3. Now, if I ask us to solve the system, what I'm really asking you to do is solve both these equations simultaneously. Well, I think you can see if we've got one equation is a line equation and the other equation is also a line equation, typically what happens is the lines will intersect somewhere and they will have a point, a single point, that will be one ordered pair solution to the simultaneous system. All right, I'm going to solve this first system graphically. Now, solving graphically is not a reliable way to grind out these solutions because your graph might not be that great. You may miss solutions that have fractional coordinates, etc. Alright, well, what I'm going to do is sketch these two line equations. And I'll make a table of values for both. And let's see, in this first equation, when x is 0, y is 2. When x is 2, y is 1, and when x is 4, y is 0. So I've got 3 points on this line equation, and I'm going to do my best to graph this equation in the xy plane. So let me draw a set of coordinate axes. When x is 0, y is 2, gives me 1 point right there. When x is 2, y is 1, puts me here. And when x is 4, y is 0. So I've got the two intercepts and an intersecting point, and I'll do the best I can to connect these dots. Hard to do this with a straight edge on the tablet. There we go. Let me kind of fill in here a little bit. Right, when x is 2, y is 1, gives me that point on the line. Alright, so this line is the first equation in the system, x plus 2y equals 4. Let me use another color now to graph the second line in this system. 2x minus y equals 3. Again, I'll make a table of values. X and y. Let's see, when x is 0, y of course is minus 3. When x is 2, 2 times 2 is 4 minus 1 is 3. And when x is 4, y can be 5, right? 8 minus 5 is 3. And I'm going to plot these points now in a different color. When x is 0, y is minus 3, puts me down here. When x is 2, y is 1. And when x is 4, y is 5. 2, 3, 4, 5, puts me up here somewhere. Alright, I'll connect the dots the best I can. Freehand. It's a line, believe it or not. Alright, depending on the quality of our graph, we may have trouble spotting the solution to both of these. Well, I think we can clearly see, even from my kind of crude diagram, that the point 2 comma 1, when x is 2, y is 1, solves both equations. Right? And I can see that the point 2 comma 1 and 2 comma 1 is in both of our table of values. Okay, so when I'm looking for simultaneous solutions to systems of linear equations, basically I'm looking for the point of intersection of the graphs of the two lines. Alright, but as we see, graphing can be a somewhat unreliable way to solve these, so what I want to do is solve these systems, solve these 2 by 2 systems algebraically. So that's what section 3.2 is all about, solving 2 by 2 systems, and by that I mean 2 equations with 2 unknowns, solving 2 by 2 systems algebraically. Alright, let's start out with that system we just solved graphically. It was x plus 2y equals 4 and 2x minus y equals 3. Solve the system algebraically. Well, there's 2 ways to do it. There's a substitution method, and there's also what they call an elimination method. I'm going to do this one by substitution for the first time out. Alright, what I'm going to do is look at this first equation and say, well, I can solve for x in terms of y. In other words, I can take this first equation, I'll just subtract 2y from both sides, and that will give me an expression in just y for x, and I can substitute that expression for x in the other equation. That will give me one equation with one unknown, and hence I can then solve for y. Alright, let me go ahead and solve for y here. I'll get 8 minus 4y minus y equals 3. I'll get 8 minus 5y then equals 3. Subtracting 8 from both sides, I get 3 minus 8 is minus 5. And I get a solution for y of y equals positive 1. So if I'm looking for a solution to this system of 2 equations, I know the y-coordinate has to be 1. This tells me that the y-coordinate of the solution has to be 1, the point of intersection, the y-coordinate has to be 1. What I have to do now is find the x-coordinate. Now what I can do is substitute this y value of 1 into either of these equations and solve for x. I'm going to pick the first one. I can say then x plus 2 times 1, letting y be 1, must equal 4, and of course x then equals 2. Alright, so my point of intersection, my simultaneous solution to both of these equations, is going to be the point 2 comma 1. This is my solution, or solution, for that given system. Alright, so that's the substitution method. Kind of a simple example. Let's try to do another one here. Something a little nastier. Again, sometimes we'll prescribe what method to use. Sometimes it's up to you what method to use. I suppose in some problems one method might be favored. Sometimes it doesn't make a difference. Right? So we're going to stick with the substitution method for now. And let me give you another system of 2 equations with 2 unknowns, a 2 by 2 system, right? 2/9 x minus 2/9 y equals 2/3. Downstairs, another linear equation. 0.1 x equals 0.2 minus 0.1y. Alright, of course I'm not going to want to deal with the fractions here. Of course I'm not going to want to deal with the decimals. What I'm going to do is take the first equation, let me label this top equation equation 1 and this bottom one equation 2. I'm going to get an equivalent equation to number 1 by multiplying through by 9. And I'll shorthand it like this. I'll say 9 times equation 1 will result in the following expression. Well, let me show it'll work here. I'm going to multiply both sides of the equation by 9. 9 times 2/9 x gives me a 2x minus 9 times 2/9 y gives me minus 2y equals, and on the right, 9 times 2/3 gives me, well, 3 cross cancels the 9 3 times, and 3 times 2 is 6. 2x minus 2y equals 6. How about downstairs? Well, clearly I don't want to deal with these decimals. I'm going to multiply equation 2 through by 10 to get rid of the decimals. And I will get x equals 2 minus y. Again, let me show it'll work here. Multiply both sides of equation through by 10. 10 times 0.1x gives me 1x, or just x. On the right, 10 times 0.2 gives me a positive 2. And of course, applying my distributive law, 10 times minus 0.1y gives me minus 1y, or just y. Alright, so here is an equivalent system. It has the same solution, but doesn't have any fractions or decimals in it. Alright, I claim this screams out to be solved by substitution. One of these variables is already solved for. X is already solved for. So I can take that expression for x, plug it into the x value in the other equation. I'll get the resulting one equation with one unknown. 2 times 2 minus y minus 2y equals 6. I'll get 4 minus 2y minus 2y equals 6. 4 minus 4y equals 6, of course. Minus 4y equals a positive 2 if I subtract 4 from both sides, and I'll get then y equals minus 2/4, which is equivalent to minus 1/2. Alright, so my solution point for both equations is going to have a y coordinate of minus 1/2. And sometimes they're fractional, and sometimes we have to deal with the fractions, so this is one of those times. Alright, I want to now solve for the unknown x coordinate, and you can plug into either of these equations the known value of y. I'm going to pick the top one. Plugging in y equals minus 1/2, I'll get 2x minus 2 times minus 1/2 equals 6. So 2x, negative times negative is positive, and 2 times 1/2 is 1. So 2x plus 1 equals 6. Subtracting 1 from both sides, 2x equals 5. And of course, x equals 5/2. So with my substitution method, I have determined both a y coordinate and an x coordinate. So my solution point for the simultaneous solution is the point x equals 5/2 and y equals minus 1/2. So I'll box this answer, claim that is the solution to the simultaneous equations, and go on to the next problem. Alright, so those are two examples of the substitution method. I want to talk now about an elimination method. Now, there are two ways to get to the same goal. Again, the idea here is to solve simultaneously 2 by 2 systems. Alright, so here's a system, and what I'm going to do is notice that I've got opposites here in my y column. Both line equations are in standard form, ax plus by equals c, but I've got it rigged so these y values, these y variables will cancel each other out if I add these two equations. Anytime I add two equations, I will get another equivalent equation. And if I rig it so one of the variables cancels out, as it does here, I'll be left with one equation with one unknown. Kind of a nice trick. So 7x equals minus 14, which means x, of course, is minus 2. So my x-coordinate of my solution point is minus 2. I now need to solve for the y variable. Now I can pick either of these equations and plug in x equals minus 2 to solve for y. I think I would like to pick the, let's see, I'm going to pick this second one here. 2 times minus 2 minus 3 times y equals minus 16. I'm using the second equation here, substituting in the known value of x equals minus 2 to get this resulting equation. So I now have one equation with one variable. I'll get minus 4 minus 3y equals minus 16. Going up here, adding 4 to both sides, minus 3y equals minus 12, and of course y equals positive 4. So I've got as coordinates for my solution x equals minus 2, y equals 4, and I would probably write that in ordered pair notation for my final answer. The solution to the given system is the point, minus 2, comma 4. Alright, that one was kind of rigged. The y variable was already set up to cancel out. It always won't be so easy. Get a fresh screen. Let's try another one. Solve. Again, I'll specify by elimination. Use a's and b's this time. 9a plus 5b equals 16. And 3a minus 4b equals minus 6. So I claim there are corresponding a-b values that will solve both of these equations simultaneously, and I want to rig it to solve by the elimination method. Well, I notice in the first equation that 9 is a multiple of 3. So what I can do is take my first equation, and I'm going to leave it alone. And I'm going to take my second equation and multiply it by negative 3. I will do that, so I will end up with an elimination of the a variable when I add these two equations. Alright, so my doctored second equation will look like minus 9a plus 12b equals 18, and multiplying through both sides by negative 3. Right, now notice the a coefficients are equal in magnitude but opposite in sign, so they will cancel each other out. 12b plus 5b is 17b, and 18 plus 16 is 34. So I can solve for b. I know what b has to be. b has to be 2. So again, typically I'll put my answer in ordered pair fashion, and usually the variables are in alphabetical order in ordered pair fashion. So I know my b value has to be 2 when I'm thinking about a simultaneous solution to both of these equations. Alright, now I can plug this value of b into either of my original equations and solve for a, I think I'm going to pick the second equation. The original second equation was 3a minus 4b equals minus 6. And if I sub in b equals 2, well, I can solve for a. So 3a minus 8 equals minus 6. 3a equals, well, if I add 8 to both sides, I get a 2. And hence I get an a value, a equals 2/3. Yes, 2/3 is a fraction, and sometimes it happens that way. So I've got a b value of 2 and an a value of 2/3. So there is my solution to the given system. Okay, the point 2/3, comma 2. All right. Let's try another one. Let's try another one with the elimination method. Solve by elimination. And this one's a little nastier. For x equals 3 times 2 plus y. And downstairs, 3 times x minus 10 equals minus 2y. Alright, you can imagine that we want to get things in standard form, clean things up and put them in standard form to make things a little easier to solve by elimination. Alright, if I look at this top equation, I can equivalently, well, if I clear the parentheses on the left, on the right hand side, 3 times 2 is 6, plus 3 times y is 3y. I'll subtract 3y from both sides and get the equivalent equation, 4x minus 3y equals 6. Similarly, I can manipulate the bottom equation. 3 times x is 3x. Minus 30 would be on the left. If I add 2y to both sides, I'll get a plus 2y, and then adding 30 to both sides, I get a positive 30 on the right. So I convert both equations, convert to standard form. Almost always helps. ax plus by equals c. Alright, I see something happening here. I think I can, well, if I multiply the top equation here, I'll call this equation 1 and this equation 2. If I multiply the top equation by positive 2 and the bottom equation by positive 3, I'll get elimination of the y variables. Let me write that down. I'm going to choose to eliminate the y variables because I see these signs here are opposite already. So again, 2 times equation 1 will give me 8x minus 6y equals 12. That wasn't too bad. Similarly, I will multiply the bottom equation through by positive 3, resulting in 9x plus 6y equals 90. I see what's happened here. I've rigged it up so that I've got opposite y values, opposite y coefficients in the y column. Hence, when I add these two equations, the y variable will disappear. I'm left with then 17x equals 102 and x equals positive 6. So I know my solution point is going to look like this. X has to be 6. And I can plug that x value into any of the equations above. And I think I'm going to pick this one. If x equals 6, I can solve for y. So 3x plus 2y equals 30. 18 plus 2y equals 30. 2y equals, well, 30 minus 18 is 12. And of course, let me scroll down, I'll get a y value also of 6. So if I'm solving both equations simultaneously, x must be 6 and y must be 6. So let me write that down and label my solution. The solution is the point 6, 6. Alright, one more. It's kind of a nasty one. It's in the upper reaches of our homework assignment. This is number 56 in the exercise set at the end of section 3.2. Solve the system. 4y plus 5x minus 7 equals 0. And downstairs, 10/7 x minus 4/9 y equals 17/21. Now, don't panic. Students tend to fall apart in this kind of problem. Don't let this happen to you. Let's get everything in standard form before we do anything else, and I'm going to clear away the fractions, of course, from the second equation. So this top equation, if I rearrange things in standard form, I'll get 5x plus 4y equals 7. Now downstairs, I want to clear away these fractions, and I believe the least common multiple of 7 and 9 and 21 is 63, is it not? So I'll multiply all terms, both sides, by positive 63. Alright, 7 goes into 63 9 times. So I'll get a 90x. 9 times 10x is 90x. Similarly, 9 cross cancels into 63 7 times. So I'll get a minus 7 times 4y is 28y. Equals, on the right, 21 cross cancels into 63 3 times, right? And 3 times 17 is 51. Alright, so without too much work, I've got it to look a lot nicer, and I think I see a way to go here. I see minus 28. Well, isn't 28 a multiple of 4? It's 7 times 4. So what I'm going to do is leave my bottom equation alone and multiply the top equation through by positive 7. You write that down. 7 times 5x is 35x plus 7 times 4y is 28y. See what's happening? Equals, on the right, 7 times 7 is 49. Downstairs, 90x minus 28y equals 51. Alright, I've rigged it up so that the y values will cancel out when I add. I get 90 plus 35 is 125x equals then 49 plus 51 is 100. So x is then 100 over 125, which of course reduces to 4/5. Alright, we're almost there. So the x-coordinate of my point of solution has to be 4/5. I don't know what y is. Alright, I think to go back, I'm going to use this equation, because I see an x coefficient of 5, and when I sub in x equals 4/5, I'll get a nice cancellation there. So I'll take this equation, and I'll say 5 times the known x coordinate of 4/5 plus 4y must equal 7. 5 times 4/5 is, of course, 4. 4 plus 4y equals 7. If I subtract 4 from both sides, 4y equals 3, and y equals 3/4. Right, so when x is 4/5, y must be 3/4, and that coordinate, that ordered pair of coordinates, will simultaneously solve both of those equations. Solution 4/5, 3/4. Alright, we're reaching the half-hour point. I'm going to call it a day for section 3.1 and 3.2, solving 2x2 systems algebraically.